1.001, 1.0001. So we're trying to get as close as it's possible to P. So let's say if you have value somewhere here, then this is going to be the secant line, yellow one. So this is corresponding to 1.5, for example. And it gets closer and closer to 1. So slope of the tangent line is defined as limiting position of MPQs as Q approaches to P, which means limit of f of x minus f of 1, this is my over x minus 1, as x approaches to 1. Now let's say for different values of x, what do we get for MPQ? So MPQ equals f at 2 minus f at 1 over 2 minus 1 equals f at 2 is 4 minus 1 over 1. This is 3. So we get 3 here. Now we can make our job a little bit easier. If we simplify this, this is basically what? X squared minus 1 over x minus 1, which is, so let's do this way, MPQ is x squared minus 1 over x minus 1. It's x minus 1, x plus 1 over x minus 1 becomes x plus 1. So x is 2, we get 3. This x is 2. X is 1.5, MPQ would be 2.5. So this is 2.5. If it's 1.1, it's 2.1. Then 2.01, 2.001, 2.0001, and it continues the same way. Now you can notice that as x gets closer to 1, MPQ approaches to 2. So it gets closer and closer to 2. As x approaches 1, MPQ approaches to 2, which implies m of the tangent equals to 2. So slope of the tangent line at 1 will be 2.
Instructor,
Yes,
values, how did you get the x values?
x values.
Yeah.
I need to get closer to 1, right?
Uh-huh.
So to next closer number, I choose 1.5, then 1.1, 1.01, 1.001. I'm making the distance between the point and 1 gets closer to 0.
Okay.
So x approaches to 1, right? In this case, it's called x approaches 1 from the right. That's what we did. But the same thing you'll get if you do from the left.
Okay. And then the line, what is the line?
So blue one is the first one, secant line, right?
Mhm.
Yellow when it already gets closer. And the red one is the one that we're looking for. This is not a problem from the book. This is just an example. We'll do from the book also. So we're trying to understand the concept. So the concept is this. So the procedure, how we're finding. Because we do not have the second point, we have only one point, right? 1, 1. To find the tangent line, we need to have a slope. To find the slope, we're choosing secant lines so that the secant lines rotates and gets closer to this one. So that means Q goes along this line towards 1. And if it goes closer to this one, so the points are here also getting closer, corresponding x values to 1. And then just algebraically we see that it approaches to 2. Say if I choose even smaller number, let's say 1.00001, would be 2.00001. So it goes to 2. Now, to understand difference between average and instantaneous values, because the one we're talking about is instantaneous value. Slope of the line of PQ is average value. So the slope at exactly 1, 1 at P is instantaneous value of the function at that point. So it's called derivative, instantaneous rate of change. The other one is average rate of change. That's what we have velocity problem also. Now let's do velocity problem that you can understand what am I talking about. Okay, so let's assume you are in a car and you are driving on a freeway. So let's say from Glendale, you go to North Hollywood, for example. So if you know what time you start your trip and what time you finish, right? Total time and total distance, you can find average rate of change. So velocity average will be distance divided time. But that's an average rate of change. For example, if you in 15 minutes passing, let's say 20 miles, 20 miles divided 15 is 140, 0.25 hours. You can find how fast you were traveling average. But you're not going with the same speed all the time. So at different points, you have different speed. If you have the driver sitting inside of the car, so you can look at the speedometer in front of you. It shows you going 55 miles per hour, 60, 70, no highway, no cars, you go faster than that, maybe 80, 85 miles per hour. If it's a traffic at certain point, you're slowing down maybe 40, 30 miles per hour. Now, instantaneous rate of change is the speed of the car at exactly at that time. Now, let's assume we have this distance. So from A, you're going to B. Now, T equals T1. Your car is at this point. You want to find out, let's say, what's the instantaneous, what was the speed of the car at that moment. Now we can do the following. So from here to here, let's say t equals t2. And let's assume st, position function, is defined as f of t function. Now average, v average between t1, t2 is defined f of t2 minus f of t1. This is the distance passed between t2 minus t1 time. But that's the average speed. Now, in order to make a little bit more accurate or like get closer to the exact value, we can make it closer interval t equals t3. Now, v t1, t3 is f of t3 minus f of t1 over t3 minus t1. But t3 value, we choose something closer. That means it becomes the time-wise is shorter amount of the time. Now, make it even smaller, closer to t1, somewhere here. Smaller the time interval, smaller is the distances. And that means V average is T1, T4 is defined F of T4 minus F of T1 over T4 minus T1. And this way we're trying to get closer and closer. If you get very close to this one, then your average velocity will be almost the instantaneous velocity at times t1. So the instantaneous, let's write it. The instantaneous velocity when t equals t1 defined to be the limiting value of this average velocity over shorter and shorter time period that starts at t equals t1. So whatever we calculate, what's happening here? So see, the time becomes closer to t1, distance becomes very close to that one, and the quotient will give you instantaneous speed, because for a shorter time you don't have much time to change your speed. So that's why we can consider kind of almost constant for, let's say, 1 second or 2 seconds or something like this. Now let's do example now from the book related to this one. Which problem? Number 6. If a rock is thrown upwards on a planet Mars with a velocity of 10 meters per second, its height in meters t seconds later is given by y equals 10t minus 1.86 t squared. Find the average velocity over the given time interval. See 1, 2, 1, 1.5, 1, 1.1, 1, 1.01, 1, 1.001. Estimate the instantaneous velocity when t equals 1. Okay, so y is equal, so this is 1.4, number 6. So y equals 10t minus 1.86 t squared. That's your f of t. Now, average velocity is f of t minus f of a over t minus a. Now, in our case, a equals 1. So we have f of t minus f of 1 over t minus 1 equals. Now, first they ask you to find average over 1, 2 equals f of 2 minus f of 1 over 2 minus 1. Find the approximate value for this one. And then find V1, 1.5, which would be f of 1.5 minus f of 1 over 1.5 minus 1. And then V1, 1.1, V1, 1.01, V1, 1.001. Find those values. So F1 is 10 minus 1.86, which is 8.14. So the first one is equals. F2 means 10 times 2 minus 1.86 times minus 8.14 over 1, which is approximately equals. Now use your calculator to find value. Keep 2 decimal places. So actually it's exactly 4.42 mile per second. Now find the value for V between 1 and 1.5. So anyone has the answer for the second part? 1 through 1.5.
Professor, I
Yes.
got 5.35.
Correct. So this is 5.35 mile per second. Not the 1 through 1.1. Keep 3 decimal places. So it should be 6.094 mile per second. Now 1 to 1.01, keep in this case 4 decimal places. You have 6.2614 meter per second. And the last one. See, closer the time gets to t equals 1, so more digits will start repeating. But this one now becomes what? 6.2 is the same, 7.814 meter per second. So we can make a conclusion. So the instantaneous velocity when t equals 1, which means when t approaches to 1, is 6.28 mile per second. Something like this. So the time interval, by making smaller and smaller, the time and distance that allows to change the speed becomes so small that we can consider that the speed is constant. So that's instantaneous rate of change. So again, if you're calculating speed of the car from T1 to T interval, time interval, then you're calculating average velocity or average speed of the car. Then instantaneous velocity is exactly at that time t equals to t1, what is the speed of the car. So those two things, slope of the tangent line and the velocity problem, are calculated using the idea of the limits. Okay, any question? Now we're talking about the limits. So let's go to the next section, which will give us the definition for the limits. So what do we understand by the limits? So we're starting 1.5. Victoria. So limits is, well, you're talking about limiting position, but now we'll talk about limits. The limit of a function. See, the top one is similar to our instantaneous velocity function, but f of x is corresponding to the graph of, let's say, x squared, 1.9, 1.99. We're approaching to 2 from the left. We're approaching to 2 from the right. 2.1, 2.01, 2.001. Then the function value gets closer to 4. From the left, it gets closer, becomes 3.999600001. From the right, it's 4.0040001. See? On the graph, G and H are different from F the following way. We calculating the limit as x approaches 2, which means from left, from right. But x is not equal to 2. So whenever we say x approaches 2, x not equal to 2. It just gets closer to 2. Now, x gets 2 from the left, x is always less than 2. X approaches 2 from the right, x is greater than 2.
So excuse me, Professor, it's the same idea as asymptotes, essentially?
No asymptotes. We're not talking about asymptotes. We'll get to the asymptotes also. How the limit, the idea of the limit will work for the asymptote. Yes. Let's say you're approaching to the number, function value approaches to infinity. You're never equal to that number. You're just approaching to that number. Let's say for vertical asymptotes, or when x goes to infinity becomes very large number, the limit goes to some number. Now look at those two graphs. The first one, 2, 4 is missing. You don't have that point on a graph. But the limit exists. The limit is 4 when you're approaching to 2 because function value approaches to 2. Look at the second one. Function value is defined. At 2 is 1. It's removed from the graph down to 1. but the limit has nothing to do with the function value. So it approaches to 4. Now, of course, the limit and the function value might be the same. So not just might be the same, that's already another important thing. See, if you have the same graph, but now it's defined. So let's say this is the graph. So let's assume this is 4, this is 2. Now in this case, limit exists equals to 4, and the function value is also 4. That's something we're going to use to determine if the function is continuous. See, first two, limit exists. First one, function value is not defined. Second one, function value is defined but different than the limit. Third one is function value and limit are the same. So you may have a hole, but limit still exists. Now, what do we understand by saying the limit of the function when x approaches to certain value? So definition is this. Limit of f of x as x approaches a equals to L. So we can make the values of f of x arbitrarily close to L, as close to L as we like, by taking x to be sufficiently close to a on either side of a, but not equal to a. So that table gives you great example for you. X approaches from the left to 2, staying always less than 2. X approaches 2 from the right, staying always less than 2. And f of x approaches to 4, f of x approaches to 4 in either case. So the limit exists. So f of x tend to get closer and closer to the number L as x gets closer and closer to a from either side. So f of x approaches L as x approaches to a. Now, x not equal to a, definition of the limit. This means in finding the limit of f as x approaches a, we never consider x equals to a. In fact, f of x need not even be defined when x equals a. The only thing that matters is how f is defined near a. Now, 3 graphs together now. First one, limit of f of x as x approaches to a is L. F at a is also L. So the limit exists and function value also defined, and they are the same. Second, limit of f of x as x approaches to a is L. Function value at a is, let's put this one m, some number m, not equal to L, but limit exists. Third one, limit of f of x as x approaches to a is L. F of a does not exist. So we do not have a value for function value. It's open circle, no value. Second one, it has, but it's removed from the graph. And the first one has the same value. But all three of them, for all three of them actually, x approaches a, limit exists. So the limit does not depend if the function is defined at that point or not. Okay, any questions?
Sorry, so the limit on the middle one is the little dot below the open circle?
Yes,
Alright.
that's the function value. Now, if we say limit exists at the point we understand from left and right, now we can talk about one-sided limits. Now, x approaches 0 from the left indicates that we consider only values of x that are less than 0. X approaches 0 from the right indicate we consider only values of x that are greater than 0. Now let's do one example. So assume f of x is a function such that it equals 1 if x is less than or equals 0, negative 1 if x is greater than 0. Now, x is less than or equals 0, function value is 1. So this is what we have. X is greater than 0, we have negative 1. This is what we have for the other part. X approaches 0 from the left means x is less than 0. F of x approaches 1. X approaches 0 from the right, which means x is greater than 0. F of x approaches to negative 1. Limit of f of x as x approaches 0 does not exist, because from left and right we approach and we get different values. Now, but if we talk about one-sided limit, let's say limit of f of x as x approaches 0 from the left, then it's 1. Limit of f of x as x approaches 0 from the right is negative 1. So left hand limit, right hand limit exist, but they are not equal to each other. That's why the limit at x approaches 0 does not exist. So limit f of x as x approaches 0 from the left not equals to limit f of x as x approaches 0 from the right. So this one tells you that in order, we'll have a theorem, of course, about this one. Function to have a limit at the given point, the left and right hand limit should exist and must be the same. Now, let's go back to our lecture notes and discuss one-sided limits. to a and x is less than a. Usually, right hand or left hand limit, we talk about endpoints. If there is an interval on which f of x is defined and we have an endpoint. If a is a right hand point, we talk about left hand limit. If a is a left hand point, we talk about right hand limit. So those two graphs are showing that. Now, important thing for us. Limit of f of x equals L as x approaches a. If and only if the limit of f of x is L as x approaches a from left, limit of f of x equals L as x approaches a from the right. From left, from right. If you're approaching to a and f of x has the same limit, then the limit exists. If and only if means in both directions. If the limit exists means left and right hand limits exist and must be the same. If left and right hand limits exist and they are equal, then the limit at that point, defined, exists. Now sometimes it's hard right away to determine the limit of the function as x approaches to a. So for certain problems, we're splitting this into two parts. X approaches a from left, x approaches a from right. Separately, find those two limits and then determine if the limit exists or not. Any questions? Yes.
Yeah. So it says if limit x of a minus, right? Is that approaching from the left?
Yes. That means x is less than a.
And then the plus one, and then limit of a plus, it means it's approaching from the right.
Correct. If you go back to the first example here, see here.
Yeah.
The left part of the table, this one is x approaches, it says like 2 from the left.
Yes.
This is x approaches 2 from the right. From the right means 2 point something. It should be greater.
Yes.
From the left, it's 1.9999. As many nines you want to put there, you can put it.
Okay.
So basically thinking about it, it's another way of writing integral notations, essentially. It's like saying you cannot equal 2, but you can go either way.
It's not included, yeah. You're getting close to that one, so it's not included. Remember, when you talking about intervals, right? Like already calculus or higher, even pre-calculus should be there. We usually consider open intervals. When you need to include the endpoint, then you need to discuss it separately. See, in this case, that's why we have left and right hand limits. So if you're evaluating limit on certain interval, it means all the points, but the endpoint should be discussed separately. Now, infinite limits. This is where we get your asymptotes. Let f be a function defined on both sides of a, except possibly at a itself. Now, the limit of f of x is infinity as x approaches to a, means that the value of f of x can be made arbitrarily large as we please by taking x sufficiently close to a, but not equal to a. So it can go positive infinity, it can go negative infinity, you can have one-sided infinity. See, first one, from the left, from the right, you're approaching, function values goes to infinity, becomes larger and larger. So the idea of this, for example, if you have, let's do one example really quickly, you can. let's say f of x is defined as 1 over absolute value x minus 3. So when you graph this equation, so at 3 you will have asymptote, and the graph will have this type of shape. From either side, when you get closer, so let's say 3.1 minus 3 is 0 0.1. 3.01 minus 3 is 0 0.01. So when you get closer, then you have 1 divided 0 0.1 is 10. 1 divided 0 0.01 is 100. 1 divided 0 0.001 is 1000. So by dividing small number, the quotient becomes very large. From the left will be negative 0.1, negative 0.01, but absolute value becomes positive. So that's why you get infinity as x approaches to 3 from either side.
Mr. Bogosian,
Yes.
I came late for 20 minutes because my internet connection was bad. Is that okay?
Okay. Yeah. Don't
Okay,
worry.
thank you.
Yeah.
Yeah, I came
It-
at 10 because
Yeah.
I just didn't miss the time.
Yeah, I understand. So it's well, I mean, it's something that it has nothing to do with you. So it may happen. Don't worry about that, guys. You can just write it in the chat and it's fine. Thank you for letting me know about that. Now, illustrated graphically goes to infinity or goes to negative infinity. So if limit of f of x as x a equals to negative infinity as x approaches a, then we have negative infinity. Remember, infinity or negative infinity are not numbers, which means the limit does not exist. So this means does not exist. So similarly, if you get here, this is also, it doesn't mean limit exists. Limit is infinity, but it does not exist because it's not a finite number. Now, if any of those cases occurs, you approach a from the left, you go infinity. You approach from the left, you go negative infinity. You approach a from the right, it goes infinity. You approach a from the right, it goes negative infinity. We have a vertical asymptote. The limit, of course, does not exist. We cannot even put infinity if x approaches a, because from left and right it goes to different values. Okay, Elton, it's okay. Now, the line x equals a is called the vertical asymptote of the curve y equals f of x if at least one of the following statements is true. So the limit of f of x is infinity, or negative infinity if x approaches a, from the left, from the right, or in general. Okay, any questions? Now we need to do examples, but we'll do it tomorrow and then continue. So 1.5 was a little bit long session. Let me just Make sure that a few people here or not. And then, now, Armstrong, Armen, Arthur. Not here. Chase, Gracia, Neil. Not here. Fabian Gutierrez. Okay, that's it. The rest of the people, I got your name, so that means you are present. Now, any question?
I have a question regarding the homework.
Yes.
Let's say if we answer it wrong, is it gonna give us multiple attempts or?
You usually have a few attempts, yeah, 3 to 5. You can try to see how it works. I mean, that part I can even change, but don't worry. I mean, if you're getting that constantly wrong, then we need to go over that problem. So you can ask during the office hours or even during the class time. So if the problem is important problem, so I'll do it like at the end of the lecture, I'll go over it. Or I'll do it during the office hours. So whatever is convenient for you.
My next question was if we answered wrong on the first attempt, is it gonna mark it down?
No, you can have like a second, third attempt, so you can try it.
No markdown?
No.
Okay, thank you.
The homework are on web assign.
Yeah, I already signed.
No, not only you, Victoria. There are
I already
asking questions, yeah. So if
sorry.
you're asking a homework question, that means you already know how to do your homework. But like some people still like asking questions. Any other question? So as soon as we finish chapter 1, it's I think 1.8 is the last session. I'll give you practice exam to get ready for the exam. And then you will have your first exam on chapter 1. Practice exam, you upload on Canvas, so I can see that you can upload your work. And then if you have any questions, we'll go over your questions, of course. It's engaged, correct, Luciana. Now, if you have any questions, you can ask me. No questions, see you tomorrow. But like in 10 minutes, I'll open the office hours. So if you have questions, you can get into the office hours and ask me question there too.
Yeah, they're on Canvas, right? You can click that.
Say it again?
You go to the office hours on Canvas, correct?
No, it's Zoom.
No, but I'm saying the link is on Zoom, Canvas.
It should be on your syllabus too.
Okay.
Yeah, it's in both places.
Thank you, Professor. See you tomorrow.
No problem.
Thank you very much, Professor. Have a wonderful day.
You too. Thank you, Sam.
We finished 1.4, right?